Hi, we're going to be working on problem 13 of practice exam 2 in preparation for exam 1 of fall 2025. This problem asks us to prove that for any irrational number x and rational number y, if xy is rational, then y is equal to 0. There are two approaches that we can take to doing this problem. One is a proof by contradiction and the other is a proof by contrapositive. I will only be going over the proof by contradiction, and the reason for that is the proof by contrapositive also contains elements of the proof by contradiction, so they mirror very much the same concepts, and I would encourage you to look at the solutions posted for the practice exam if you really want to see the contrapositive solution, but it is very similar to the contradiction solution. So as long as you understand this process, you will also be able to use the contrapositive method for this proof. So in order to start a proof by contradiction, we're going to start by assuming the negation. So let's assume that the negation is true. Let's assume the negation. There exists an irrational number x and rational number y such that xy is rational and y is not equal to 0. Okay, let's break down how we were able to find this negation, and let's break it down into 3 parts. The first part is the quantifiers. Then moving into the if-then statement, we have the if portion, and then we also have the then portion of this statement. Okay, so prove that for any irrational number x and rational number y. The for any in this part should hint to us that we're talking about a for all quantifier, because this applies to any irrational number x and rational number y, and so therefore it applies to all of them. So negating a for all gives us a there exists. So we have there exists an irrational number x and rational number y. Moving into the if p then q portion, if we want to negate an if p then q, in this case our p is xy is rational, our q is y equals 0. If we want to negate this, we have p and not q. Why is this the negation of an if p then q statement? Well, when we say if p then q, we say that if p is true, then q absolutely has to happen. But the negation of that would be to say that p does happen, but q doesn't happen. And this is happening at the same time. So we're using an and here as opposed to an if then, because we're saying that these are definitively happening at the same time. So we have if xy is rational as our p, so we're going to keep that the same, xy is rational. And then we have y is equal to 0 as our q, but we're going to negate that. And so we're going to say y is not equal to 0. Note that over here, which is really important, is we're using and rather than if then, because we're saying that these conditions are occurring simultaneously. This is going to be really important for knowing how to negate if p then q statements. Okay, so let's get started. We know that xy is going to be rational by our assumption over here. So let's say let xy equal a over b, and we know that y is going to be rational as well. So let's say y equals c over d for integers a, b, c, d, where we know that a, b, C, and D are not going to be equal to 0. Or actually, I wouldn't be able to say that, or actually, sorry. Because we're saying that as an assumption here, that would be all right to say, because we know that y is not going to be equal to 0, and that's not allowed. So where A, B, C, and D are not equal to 0. So then we have xy is equal to A over B, x times c over d, just substituting this value for y, is equal to A over B. What we're going to do is we're going to multiply both sides by d over c. So we're going to have x is equal to AD over BC. The integers are closed under multiplication. That basically means that multiplying an integer by an integer will give you an integer result. We can depend on this and we don't have to prove it. So this means that since AD and BC are integers, this means x is going to be rational. This is a contradiction because we defined over here that x is going to be an irrational number. And just to make it clear, the reason that we were able to say this in the first place is because reason that we were able to say these things in the first place is because this is the definition of rational numbers. Having an integer divided by another integer, you have a rational number. So there is a way to do a proof by contrapositive. It is very similar to this method, so I would encourage you to check it out through the instructor solutions. Let us know if you have any questions on Piazza, and good luck.